Hey everyone, look, in my 30 years walking the plant floor, I have literally seen it all. And today I'm going to walk you through a complete masterclass in this explainer. We're going to diagnose and fix one of the absolute most critical issues we face, declining reverse osmosis recovery rates, specifically right here in the ultra-pure water or UPW environment. Now, if you're an operator, you already know that when your permeate flow drops, you aren't just losing product water, right? You are bleeding money and you're putting a massive amount of stress on your entire system. So today, I want to share the exact methodology I use to troubleshoot these failures, step by step. By the end of this, you're going to be able to confidently step onto your plant floor and keep your systems running at absolute peak performance. So, we are going to treat this system failure exactly like a forensic investigation. We'll be hitting 6 key areas today. First, RO in ultra-pure water. Second, the incident and symptoms. Third, hypothesizing the suspects. Fourth, diagnosing root causes. Fifth, the cure and troubleshooting. And finally, number 6, summary and debrief. Let's just dive right in. All right, phase 1, the baseline. Let's quickly review RO technology in ultra-pure water. Now, before we can actually fix any problem, we have to establish our baseline. Because let's be real, you simply cannot troubleshoot what you don't fully understand. Think about the sheer massive scale of a fully assembled RO system in a standard UPW process. The raw water doesn't just magically hit these membranes directly. No, it runs a huge gauntlet of pre-treatment first. We're talking multimedia filters, or MMF, and then those highly precise 5-micron cartridge filters way before it ever reaches the main skid. This RO system, it is doing the heavy lifting. It's stripping out both dissolved and undissolved impurities under immense pressure, preparing that water for the final mixed bed polishing stage.
Okay, if you remember absolutely nothing else from today's explainer, remember this word, recovery. Recovery is the exact ratio of your usable product, that pure permeate flow, to the total volume of feed water entering your system. And when this ratio starts to drop, well, the consequences compound fast. We aren't just losing product water, we're actively wasting valuable feed water and honestly putting a ridiculous amount of unnecessary mechanical strain on our high-pressure pumps. So a drop in recovery isn't just a hiccup, it is the very definition of an operational failure that needs your attention immediately.
You know, osmosis naturally wants to flow from a dilute solution into a concentrated one. To reverse that whole process, we have to apply external pressure. I mean, pressure significantly higher than the natural osmotic pull, using a heavy-duty high-pressure pump. This immense force literally shoves the feed solution against the semi-permeable membrane. The water molecules that successfully push through, that's our highly purified permeate stream. The water left behind, holding all those concentrated salts and impurities, becomes our reject stream. It's a delicate hydraulic balance, and if it gets disrupted, we've got a major problem on our hands.
Moving on to phase 2, the symptom. How do we actually identify the failure state?
Let's talk about the exact symptoms of a system failure. How do we really know when things are going off the rails? Well, the most common mistake I see operators make, literally all the time, is ignoring the early warning signs. In a perfect design state, your permeate flow is rock solid and your reject volume does exactly what your calculations say it should. But when you hit a failure state, you're going to notice your recovery rate tanking below your design specs. Suddenly, your reject water volume spikes out of nowhere, and boom, you've got a critical shortage of permeate. You're pumping the exact same amount of feed water, burning the exact same amount of electricity, but getting way less usable product. So, here is the crucial point. The magic number, 15%. The absolute golden rule in the water treatment industry is this: if you see a 10 to 15% decrease in your normalized permeate flow, or a 10 to 15% drop in permeate quality, or an equivalent spike in pressure drop across the stages, your system is practically screaming for help. Notice I said normalized data. You absolutely have to account for daily temperature and feed pressure fluctuations to see what's really going on. If that properly normalized data drops by 15%, believe me, fouling is actively happening inside those pressure vessels.
Which brings us to phase 3, the suspects. Let's hypothesize the causes of this fouling.
Let's look at the usual suspects. What exactly is choking our system? Well, we have a pretty familiar lineup of notorious offenders. First up, hard inorganic scales like calcium carbonate or sparingly soluble sulfates, think barium and strontium. Then you've got metal oxides like iron or manganese, which will instantly precipitate the second they're oxidized. We might also be dealing with polymerized silica or even tiny colloidal deposits that manage to sneak past pre-treatment. Over on the organic side, natural organic matter like humic or fulvic acid from surface water can quickly form this thick, suffocating gel right on the membrane.
And lastly, bacterial bioslime. Now, a single bacteria replicates roughly every 20 minutes in the right conditions. That means a tiny biofouling event can spread like wildfire and get completely out of control fast. And here is exactly where those suspects love to hide, inside a spiral-wound membrane. The architecture itself is basically a trap. Suspended solids and colloidal matter love to get wedged right into the feed and brine mesh spacers. Those are the tight, cross-hatched layers keeping the membrane envelopes apart. The second that mesh spacer starts clogging, it severely chokes off your cross-flow velocity. Your pressure drop instantly shoots up, the water flow is physically blocked, and you end up completely starving the central permeate tube of the product water you desperately need.
All right, phase 4, the diagnosis. Investigating to eliminate those false leads. Now we step into the diagnosis phase to hunt down the true root cause. But this presents a real practical challenge out on the plant floor. Obviously, we can't just slice open a sealed membrane element while the plant is fully pressurized and running. So how do we confidently figure out what's destroying our recovery rate? Simple. We have to rely entirely on the operational data. We do that by using a systematic troubleshooting matrix, exactly like this one. We take our normalized pressure drop, our feed pressure, and our salt passage data, and we correlate them to pinpoint the culprit. Let's say you see a normal to low pressure drop, but a high salt passage. Well, you're almost certainly dealing with inorganic mineral scale physically damaging that membrane surface. On the flip side, if you're looking at a really high pressure drop, but completely normal salt passage, you've probably got an organic or biofouling problem that's choking up the feed spacers, but the rejection layer itself is still okay. Guys, the data always tells a story if you just take a minute to read it.
But listen, just staring at the membrane data isn't enough. You've got to play detective and look upstream. Are we accidentally creating our own problems? First thing, calculate your Langelier saturation index, or LSI, right in the reject stream. If it's creeping above -0.2 and your antiscalant dosing pump has lost its prime, congratulations, you are actively manufacturing calcium carbonate scale. Next, double-check your feed turbidity. It has to strictly stay below 1 NTU. Then look at your silt density index. It absolutely must be under 2 for borewell water and under 4 for surface water. Finally, go physically inspect those 5-micron cartridge filters. If they're bypassing or failing, your insanely expensive RO membranes just became your new multimedia filters. And that is an absolute nightmare.
Okay, phase 5, the cure. Let's get into the detailed remediation procedures. So, we've cornered our suspect and verified our upstream conditions. Now, it's time to administer the cure using a highly specific clean-in-place, or CIP protocol. First, you absolutely have to know what you are cleaning. It's super common to use multiple chemicals in a very strict sequence. If you even suspect mixed fouling, always run your high pH wash first. That strips away the organics, oil, and bioslime. Only after that do you run a low pH acid wash to dissolve the leftover mineral scales and metal oxides. If you do this backwards and hit organic slime with acid first, you'll likely polymerize it, essentially baking it permanently right into the membrane. Oh, and basic safety check here. Always add your chemicals slowly to the batch tank and never ever mix your acids directly with caustics. Now, I want to pass down a couple of veteran tricks I've hammered into my crews over the decades. When you're cleaning a multi-stage system, clean it one stage at a time, period. This focuses all your pump energy and keeps your flow velocities high enough to aggressively blast those foulants out of the spacers. Also, always make sure your cleaning flow matches the normal feed flow direction. If you try to reverse it, you can cause telescoping and permanently destroy the element. And here's an incredibly simple preventative trick. Whenever the plant is shut down for a prolonged time, soak your elements in pure RO permeate. That ultra-pure water naturally dissolves mild scale and loosens up stubborn precipitates, all without needing a single drop of harsh chemicals. And finally, phase 6, the debrief. Let's talk summary and prevention. Let's step back into the control room for a minute. Troubleshooting is fantastic, but prevention, that's the real game changer. If you only take away one thing from my 30 years of experience, let it be this golden rule. Clean when the system is lightly fouled. Do not wait for heavy fouling. Getting in there early is literally the only way to save membranes over the long haul. Because if you sit around waiting until your normalized performance drops 30 to 50% before firing up a CIP, that heavy fouling turns into a physical shield. Your cleaning chemicals won't be able to penetrate the foulant layer, and the mechanical damage to the membrane is pretty much irreversible at that point. So I'm going to leave you with this final practical question to chew on. Tomorrow morning when you walk out onto the plant floor, grab your clipboard and look at your RO skid. What is the very first normalized metric you are going to check to protect your recovery rate? I highly suggest you keep a disciplined eye on those pressure drops, watch your salt passage trends like a hawk, and absolutely never ignore that 15% warning threshold. Thanks for hanging out with me for this explainer on RO system recovery. Keep your membranes clean, keep your data normalized, and keep that permeate flowing. Catch you next time.